Okay, so coming back where we left off last week with regioselectivity. So as a reminder, when we do radical chemistry and we're doing radical halogenation, we are adding bromines or chlorines. Fluorines are too reactive, iodines are not reactive enough. So when we add these bromines and chlorines, they are regioselective because we have to form a radical. And radicals are not stable intermediates. So they follow the same pattern as carbocations. Tertiary are going to be more stable than secondary. Secondary are going to be more stable than primary. And if you can form a radical that has resonance to it through like in an allylic position or benzylic position, that affords more stability, and that's even better. And what we find is because of this combination of stability is that chlorine prefers tertiary over secondary, secondary over primary. But it can halogenate any one of those. Now, however, when we talk about bromine, bromine is extremely regioselective. And if there is a tertiary carbon, it will always add there. If there's a secondary, it's going to add to your most substituted carbon every time. And that's just something you have to be aware of. Okay, now that we talked about regioselectivity, and regioselectivity, remember, is the fancy word for saying it has a specific carbon it wants to go to. Now we're going to talk about stereochemistry. So when we have stereochemistry, when we form stereoisomers, there are two possibilities in the world. Either A, we make a stereocenter and it's stereospecific, meaning we are going to invert, like it was an R before, now it's going to be an S or something along those lines. Or we can make a mix of R and S. And do you remember what that combination is called when you make a mixture of R and S? If you don't worry about it.
No.
Okay, so remember, if you make a mixture of R and S, and it's in 50-50, it's called a racemic mixture. It's half R, half S.
Oh.
And you make racemic mixtures in particular cases. The first example that we learned about them was carbocations. And what we're going to find here is that if we do make a stereocenter when we do halogenation via radical mechanism, we are going to make a racemic mixture, meaning we are going to get both the R and S product every time. So for example, in this one, we're adding chlorine via this radical mechanism. And if we add it here, this is going to be a stereocenter. So we can make both the R and the S. If we add the chlorine to the outside one, that's not going to be a stereocenter, so we don't have to worry about it. Again, this is only if we are making a stereocenter. If you look at our stereochemistry, if you remember, when we make this radical, we say that it has an sp2 hybridized stereochemistry. This is its geometry, right? Or we say it's a very, very shallow pyramid, right? And the idea is that we can think about this, is that this radical, when it goes through, because it can go through to either side of this orbital, is that when it goes through, it kind of inverts it, or it can just go through and it doesn't change the geometry. So because this radical can exist in either the top or the bottom lobe of this empty orbital, you can add from the top, you can add from the bottom, and that's why we get a stereo racemic mixture. So when we think about, there's actually a total of 3 monosubstituted products formed in the halogenation of butane. So imagine, and I'm going to ask you this question real quick, we'll go to the whiteboard, is that if we were to take butane and we were to do a radical halogenation in, what are the 3 products you're going to get? So I'll give you like 30 seconds to work on this. And I'm going to hit pause on the record just so it doesn't take time. All right, so coming back here, is that when we do a radical halogenation with chlorine, we can add to any carbon. It's going to prefer the secondary, so we can add to either here. Let's see when that happens. Or we can add to here. So when I add to here, I'm going to make 1 chlorobutane. And because it is here, there are 3 hydrogens to begin with. There are 2 when I put it on. This is not a stereocenter, so this will simply be 1 chlorobutane. I don't have to worry about any stereocenters there. Now, when I add to here, I can add that it is in the R conformation, or I can add if it's in the S conformation. And so this would be 2R, 2-chlorobutane. And then if I did the same thing down here, it would be essentially the same thing, except now it would be 2S. So this is why whenever you do a radical mechanism and you create a stereocenter, you have to have both the R and the S conformation possible. So as a quick follow-up, since you're the only one here, and I apologize, but if I did this reaction again, but instead of chlorine, I did it with bromine, how many products would I get?
Only one.
You'd get 2.
Oh.
Because remember,
wouldn't it be like
you would still get the R and the S.
Right.
Because it would, if you added this here, you would add to this carbon, right? It wouldn't matter if you added to this secondary or this secondary, it would still be the same thing. But in this case, you would either make the R bromobutane or the S. So don't forget, if it is to a stereocenter, it's always going to be RS if you create a stereocenter. All right, so let's go ahead and go back to, okay. So now, in the halogenation of S3 methylhexane, the chirality center is the most reactive carbon in the molecule. And so when we think about this, if we look here, how many products do you have in this one?
You have 2.
Yep. And so it's going to be E, right? Because your bromine is going to add to your tertiary carbon, which is right here. And so you're going to add either in the S conformation or the R conformation. Right. Question? Okay. So now up to allylic halogenation. So when we talk about carbon-hydrogen bonds, the lowest BDE, it's chemistry is always a game of the lowest energy. So in this case, when we do this radical halogenation, when you put in a radical, it's always going to abstract the hydrogen that's easiest to break. Essentially, it's going to break the lowest energy bond first and foremost. So in this case, we have a double bond, a carbon that's the hydrogen that's on a carbon allylic to the double bond, and then a carbon that's 2 carbons away. So when we do this, we see that if trying to put it on the double bond itself, a radical, is not great. It is extremely terrible to put a radical on an sp2 carbon. It just is not fantastic to do. Next, if we look at a carbon that is just an sp3 that's not allylic, it's better. But if we put the radical in the allylic position now, if we abstract this hydrogen, that's even better. So what we find is that if we make a radical in the allylic position, it's going to be the lowest energy to break that. And the reason for that is because when we do this, is that we're going to have resonance now with our free radical. And so if you remember back to your homework this week, you had to show that when you have a double bond nearby, right, you can move that double bond over. So coming down here to this next one, we think about hydrogen abstraction, the allylic hydrogen results in resonance. So when you take this and you remove this and you make the radical, now, right, you can move that double bond over, and now the radical is going to shift over here. So you have this resonance. This is called an allylic resonance. So these are always very reactive, and they're great to go. And so when you do this, though, you have to be careful, because when you do Br2 and a double bond, if you remember, do you remember when you did Br2 and a double bond, do you remember what happens?
Maybe, I just can't really.
You add a bromine across the double bond. Remember, there's a bromine on each carbon, right? So what we have to be careful of is that if I try to add a Br2 to here, right? And so I did Br2 and then heat or light, right? Mm-hmm. What's going to happen is maybe I'll make this and I'll make my radical, or another possibility is that I can add bromines across that double bond. And that's not what I want, right? I only wanted to add one bromine if I wanted to do the allylic halogenation. So not only did I not add one bromine, I also added it in the wrong place and I got rid of my double bond. So chemists, of course, saying, well, we want to be able to do this, so how do we fix it? Someone at some point came up with a wonderful thing called NBS, N-bromosuccinimide. So you see here, this is succinimide right here. Normally, if you think about regular succinimide, just regular succinimide that you would get, just this 5-membered ring with the nitrogen and 2 oxygens, this would be a hydrogen. But NBS is replace that hydrogen with the bromine. So now what happens is that when we make this and we hit it with light, we make a Br radical, and then we make this radical. So which one of these two do you think is more reactive? This succinimide radical or this bromine radical?
The bromine?
Yep, because this succinimide is stabilized through the radical. Because you have these double bonds here, and so you can stabilize that radical, and it's a lot better than this. So since this is more stable, this is going to be less reactive. So now when I do this, I don't have to worry about putting a Br across my double bond. I just get my radical Br and it's good to go. So this is how you would add a bromine in the allylic position. And we're going to go through and talk about, well, what does that mean for me, Maggie the chemist? All right. And so basically this is the same idea again, where we're just going to go through that propagation where you're going to do the hydrogen abstraction again, then you're going to add the bromine. And essentially what's going to happen is that you are going to make this, you're going to only add to the allylic position. So as a general statement, and I'm going to go back to the whiteboard just to show you what I mean, is that if I have this right here.
So
like this,
a question.
Right? Mm-hmm.
I have a question. Basically, you can't get rid of the double bond here.
Yeah,
because that'll make it unstable, right?
Correct. It's not that it won't make it unstable. It's just that it's not going to react the way you go. So if I hit this with light or heat, I have two possibilities. I'm either A, going to keep my double bond and add a bromine like this, or I'm going to lose my double bond and now I'm going to have bromines like this. This is an either or. I'm going to get a mixture. There's no one set. However, if I do this now, if I say, well, what if I hit it then with NBS and light like this, or heat? Now I will only get the allylic position and I will keep the double bond. I don't get that other product.
Okay.
Does that make sense?
Yes.
So the best part about this is that I keep my double bond, I add a halogen, life is worth living. So whenever you do any reaction like this here, when you can get multiple types of products, it's one thing to get multiple types of stereocenters. That's not ideal in the real world, but in your terms of thinking chemistry, like, well, if I get a stereocenter, I can't do much about it, but it's not so bad. But when you get two completely different products, this just becomes very bad for you. You want to always think, what can I do to always ensure that I just get one product? Does that make sense?
Yes.
Okay. Other questions?
Okay. That was it.
Good question. Okay, so now when we do this allylic halogenation, we can add that bromine, because we have the resonance, right? We can add it in two different locations. So because of that, we can make isomeric products. So if I did this reaction here, what's my most likely product? Or what are my products?
A.
A is going to be my most likely product. That is correct, right? I'm going to add that here. But what else could I make?
Maybe B.
Oh, no, it's just asking for the major product. Yep, and you don't have any other minor ones. Yep, so this would be your major product, right? Because you would add the radical here, correct? Because it's the bromine.
Uh-huh.
But the only other issue is that I don't like this question.
So would the minor product be B?
The minor product would be no, because the radical this you don't the minor products aren't on here at all. There's actually
Oh,
three.
okay.
There's actually two minor products, and technically A is a stereo center, so there should be two answers here for A. But don't worry about that so much. So
Okay.
now when we look at this one here, right? What is the major product of the following reaction?
Um, wouldn't it be A since you're
Yep,
adding that bromine?
we're adding it to the allylic position, right?
Mm-hmm.
So we would add it here, but don't forget. Oh no, that's it. Because there's no what on this carbon down here. This is an allylic position too, but there's no hydrogens.
Right, because there's only carbons.
Mm-hmm. All right. Okay. So atmospheric chemistry and ozone. So did you guys talk about this a lot?
Not really. She just mentioned it.
Okay, but basically this is something I talked about last week, right? Is that when we live far away, but not so far away from a nuclear fusion reaction occurring, right? And it's not great for us, the cancer and all that good stuff, right? So
Mm-hmm.
because of that, that light that's coming from that reaction, those photons that are being shot out at different energies, that radiation is bad. Now, a lot of the radiation that we think about, like the gamma and all that other stuff, gets deflected by our ionosphere and other stuff, but the UV photons can still come through. However, our layer of ozone that's at the very top of our atmosphere, well, not the very top, it's somewhere up there. I'm not a space person, but we have a layer of ozone, right, somewhere in our atmosphere. And the idea is that when that UV light comes in, it can hit and react. And so what's going to happen is it's going to turn this ozone into oxygen and into a radical oxygen species here. All right, we're going to pop an oxygen off of that ozone. So O3 is going to form O2. And now what's going to happen is that you see here, if I did two of these, what are these two things? If I did this again and I made another one of these, what's this going to form? It's going to form
Another
another
radical.
oxygen.
Oh.
So basically, when light hits that ozone, it forms oxygen and this radical monooxygen. But then if it hits another one, I'm going to make another O2, but then I'm going to make a second one of these, and then that's going to form an O2. So I'm just going to keep forming oxygen up there. There's a bunch of other stuff that's happening, so I'll regenerate ozone. But the idea is that this ozone at the top is doing a bunch of radical chemistry that's helping, it's absorbing that harmful UV radiation, right? And then giving off the excess energy in the form of heat. So the energy that's used to break the bonds forms the radicals. They go about their business, giving off a heat. It warms up our atmosphere. But that harmful radiation energy, we're stopping most of it, right? But this is why you still want to wear sunscreen when you're going out, because you are still getting some of those photons that are
Right.
coming through, right? The leather bag theory of skincare, right? And so
Skincare.
now, what you find is that back in olden times, before you were born, we used to have these things called chlorofluorocarbon (CFCs), and they used to be in things like refrigeration and stuff like that. And so basically Freon, which is what we used to use to cool, like for our refrigerators to work and stuff like that. These right here, if you look over here, you make these radicals, and then these radicals go up into the atmosphere, and then they essentially eliminate our ozone. And so if you get rid of the ozone, you're losing a vital area of protection for that UV light, right? So our use of these CFCs, or basically the freons, was just destroying our ozone layer. So we ended up making this huge ozone layer over the South Pole. And what we found out, though, is that as we stopped using them, I want to say like in 99, like we had an international agreement to stop using them because it was bad. But since then, the hole over the southern hemisphere, or over the South Pole, is fixing itself. It's closing. That hole in the ozone layer is no longer there, or it's smaller. So by removing our use of them, it makes life a lot better, right? So the ozone layer protects us from harmful what?
UV
Yep, and
light.
refrigerator. Yep, it's going to protect us from ultraviolet. And then the ozone layer has been depleted by chemicals released from air conditioners and refrigerators that will generate what? Bromine or chlorine?
Chlorine.
Yep, chlorine radicals. Just remember CFCs. There's no B there. All right, and so
Chlorine.
this is something we also talked about here. It's the same idea of this mechanism, is that if we add HBr, right, we add the Br to the more substituted carbon, it's Markovnikov, but if we do it in the presence of a peroxide, it then becomes a radical mechanism, and then the Br gets added to the less substituted side. Make sense?
Yes.
And I think you guys did this one for your last test, right?
Yeah.
Okay.
We did peroxide.
Yep. So basically what's happening is that your peroxide is going to take this hydrogen from your HBr, and then you're going to form that Br radical. And now that Br radical is going to react with your double bond. So when I come down here, if you look here, you see right here, this double bond, you're going to form a bond to the bromine, right? So you're going to have the fish hook, and then this one is going to go here. And so you're going to form a tertiary radical, right?
Right.
And so what ends up happening then is that when you do this, then you're going to form this radical here. You're going to form this more stable one, but then the carbon radical could also do a hydrogen. What's going to happen next is that it's going to do a hydrogen abstraction with another HBr. So the first HBr forms the Br radical. It attaches to the double bond. Your next HBr is going to interact with the radical, and now you're going to form your product. So now your Br and your hydrogen are flipped, and it becomes anti-Markovnikov because instead of adding the hydrogen first when we just do HBr, when we do HBr and peroxides, we add the bromine first, and that's why we do that. Does that make sense?
Yeah.
Okay. All right, and so then we see here our anti-Markovnikov addition. Again, at the end, we're going to have two Br radicals when we're finished with this. They're going to come back together, they're going to couple, and this will terminate. This is our termination step. And this is just it. And so talking about our addition again, our delta G, our enthalpy and entropy. When we think about this, we always have to consider what's the energy of the bonds breaking and forming, and what is our entropy, what's the entropy occurring in this reaction. And so usually when we think about the entropy, our entropy is not going to change much because we aren't changing the number of products and we're not changing phases as readily. So it should stay the same. So basically what's going to happen is that it's all going to be based on our relative entropy, essentially what's the energy of the bonds that we're breaking versus the bonds that we're forming. So we don't have to worry so much about entropy, it just becomes enthalpy. Enthalpic. I like saying the word enthalpic. Could be one of the fanciest words I know. All right, so basically when you do this, we can form new chiral centers. If you do form a new chiral center, right, you're going to get a racemic mixture. So if I do this reaction here, which one's my product?
D, because you're adding it to the less substituted.
Yep. And do I have a stereo center now?
Yeah, no.
Yes.
Yes.
Mm-hmm. Because this carbon right here has a hydrogen, a methyl, a CH2 bromine, and then a CH2CH3. So this is now a chiral center. So you would get this R and S, because whenever you make a new chiral center, you're going to get both.
Both.
Mm-hmm. All right. So what are the products of the following reaction? So this is a better one here.
I think for this one, I said it was, I don't remember if I said it was A. I think I said A and B, but then she said it was wrong. She said it was all of them.
So real quick, where's the bromine going to add? Which carbon? The left of the side of the double bond or the right side of the double bond?
The left side.
The right side. That's where the bromine adds. Of the double bond. Right?
Yes.
So basically here, I'm going to just come in here and annotate. This is where the hydrogen is going to be added, right? And then this is where the bromine is going to be added, correct?
Yes.
So looking at my products, A, B, C, and D, are my bromines all on the correct carbons? Mm-hmm. Are my hydrogens all on the correct carbons? Okay. Yeah. How many stereocenters am I creating when I add this?
2.
2. So, and you're asking yourself, But Terry, how do I know how many isomers I'm going to have possible answers? If you think about how many stereos you are creating, you take 2 to that number. So in this case, 2 to the 2, right? Because I'm creating 2 stereocenters. So that means you should have 4 possible answers.
Tricky.
Yes, you'll learn more about this as we go through. Now, that's the max number of answers. That doesn't mean that you're always going to have 4, but you can have a max of 4. But the way I would think about it is looking at this problem again, and for you boys and girls at home, is that when we look at this, the bromine and the hydrogen are added to the correct centers, right? They're added in the right places. They're not different. Now, since the bromine can add here, it can make any stereocenter. So it can be a wedge, it can be a dash, right? So that is correct there, right? There's no stereospecificity. Wedge or dash, it's going to make both. Same when I put the hydrogen here, is that the hydrogen is going to be on the dash here, but I can also put it on the wedge. There's no saying what has to happen. And so when I think about this, wedge or dash, these are all possible. Does that make sense?
Yes.
Or you a little, does that take, you need time to process?
No, I think I understand it.
Okay. So just remember that for every stereocenter you make, 2 to whatever power that is. So if you were making 1 stereocenter, it would be 2 to the first power, and you would only get 2 possible products. If you're making 2 stereocenters, it would be 2 to the second power, so you could get 4 possible products. If you did some weird reaction where you ended up creating 3 stereocenters, it would be 2 to the third power. So then you could have 8 possible answers. I doubt she would ever give you a question like that, so don't sweat that. That's just showing you what that is. All right. And finally up is radical polymerization. Radical polymerization is what we use in a lot of industry to make things like nylons and plastics. Very useful for a long time, but as we find out, plastics aren't great for us, right? So now when I do this.
Turtles. Save the turtles.
So when you think about, I mean, you don't know that. I mean, all right. So basically when we do this radical polymerization, essentially we are just making repeating units. So when we do this, we're going to follow that same idea of we have an initiation step, we have propagation steps, and then we have termination steps. But when we think about polymerization for plastics or whatever, usually our propagation steps are a lot. We want to make big, large things. So we have the same idea where we start with some type of, in this case, peroxide. We add heat, we do this homolytic cleavage, and now we form 2 radicals. And now when I add across this double bond, I'm going to do my first propagation step. Now I'm going to add 1 side OR, and now I've created a radical. So then if you look here on the next propagation step, I add another double bond, another ethylene, another ethylene, another ethylene. And I just keep going and going and going and going and going. And this is how polymerization works, is that I just keep doing these repeating radical steps, and I can make large polymers like plastics and other stuff like that. Right? And so now these radical polymerizations will continue until they come across another radical. So either it's going to come across another OR and it's going to terminate, or it can come across another radical of the same species. So you may be saying to yourself, well, how exactly do I make the correct shape that I want to make? Or how do I, if I want to make something that's so many carbons long or stuff like that? You don't. It's a guess. You have to say, if I run this reaction for this amount of time at this proper ratios, this is about the average size of the polymer you're going to get. So you won't get specific lengths, you will get averages. And so if you look here, you can even have things like branching happening like this. So if you have things that are highly branched, you start getting stuff that's very flexible. So things like your squeeze bottles that you can actually bend. If you have unbranched molecules like this, they're just rigid. They're going to be more of your harder plastic. So there's a lot of ways that. Yep. So then there's lots of ways that we can do that we can figure out, well, how are we going to make this plastic? And there's a whole branch of science that's been dedicated for this for almost a century now. And so when we think about this radical polymerization, right, you can take propylene or styrene. And so with propylene, you can make things for carpet fibers, appliances, right? Or if you do stuff with styrene, it just depends on what you're using as your monomer. So when you think about your monomer here, if you look at your monomer, it's just repeating units. So when we see this number here, N, that just means how many of those repeating units there are in your polymer. So if you said like, polystyrene N2000, that means that you have approximately 2,000 repeating units of that. And so, each of these things is going
to. How do you make it stop? Like, how do you make?
So when you go through, but basically, imagine that you put in all your stuff in this chamber and it's mixing. To end it, you can put in stuff that terminates radicals, or you just add in a whole bunch of other free radicals at the end. Basically, eventually, depending on the mixture, you're going to run out of things for it to react with, and it's going to have to start ending the reaction. Okay. There's only a finite number of things, so there's a lot of calculations you can do to figure that out. But basically, just know that this continues until it hits those radicals.
Okay.
You can do this type of stuff that we do in this free radical petroleum processes. So if you make like hydrocracking and other stuff. Carbon chemistry is very useful for a lot of things, but unfortunately, we've just been really bad about it. We've made so many terrible things on this planet, but you can still do this to make all sorts of stuff. And we use it in so many different fields, basically in the oil industry, in which all of our stuff arises from, like gasoline and plastics and all the petroleum industry. And then all of our plastics and other stuff arises from that. And then finally, synthetic utility of halogenation. So this is something I mentioned our first week here. Last week when we talked about this, if I ever have an alkane, what's the only type of reaction that you can do to put something on an alkane? Radical halogenation. So if you ever have a compound that only has carbon, hydrogen, single bonds, the only starting step you can take is NBS or something like that and light. This would be your recommended first step. It has to be some type of radical halogenation. And then once you go from there and you put this bromine, you could do substitution reactions, you can do eliminations, and you can do additions. And so when you get to your second semester of organic chemistry, I know you're super excited about it, and you have to do synthesis problems, and you start with an alkane, this NBS and light is your go-to step all day, every day. And so then here is a summary of those. Any last minute questions?
I don't think so.
Okay, so for those of you at home, this Thursday, I will be working on the, I'll be starting the NMR on Thursday. We'll possibly meet Saturday, and then we'll definitely meet next Tuesday. Thursday and Tuesday, definitely. But Saturday, we'll put in as the maybe. And then after that, it's finals time, and we're just going to review for the finals. So then after that, we'll just start working on the final and get you guys ready so that you can get your A's and you can move on to brand new and fantastic stuff. So I will see most of you on Thursday if you're watching at home.